So everybody knows Wikipedia, but Scholarpedia has not quite taken off in the same way as you might imagine. Let's see if we can search for this one. And let's see. Yeah, so here's a picture of what we just saw. Okay, yes, so here is a picture here of going around in just that way. Okay, that's a point that is going around and coming back here. And the density of points here is that it's slow. These points are taken at equal points in time, and so it's slow coming back down. But let me introduce the next topic, and you will see what that really is, because that's not quite really what that is. Let us put the space back in. Okay? So every point has its own f and g value. So here's a point, and it has its own f and g value. And if it is excited, if it's in the excited state, if it's here with 1, it gives a little bit of, that's what diffusion is, it gives some, and its neighbors are not, it gives a little bit of itself to its neighbors. Right, that's what diffusion is. You have a peak like this, and you give some to your neighbors. Supposing on one side you have, indeed, neither of these two are excited, the ones on the left and right, that's the situation I'm setting up. I have an excite point. But supposing they're not excited in two different ways. One of them is refractory, and one of them is excitable. Diffusion is symmetric. You give the same amount of yourself, left and right. But this one here, that's refractory, he needs a whole lot to get himself excited. So the little bit that this one gives isn't enough to get him excited. Whereas the one on the right, if he's in the excitable state, then that little bit that you gave to that neighbor is enough. Shows the right way? No, it's the opposite. Sorry. I mean, I'm seeing a mirror image of what you're seeing. Right. So here's the excited one, and so here I am. I give a little bit. I give the same amount to my right and my left neighbors. Not quite, because I'm giving proportional to the gradient. So I'm actually giving a little more on the left than on the right. But still, I'm giving some amount here. If this one here is in the excitable regime, then just that little bit is going to kick him off and be excited. If he's in the refractory regime, let's say he's sufficiently far away from being able to excite that he doesn't get excited, and hence my excitation moves to in that direction. And then that argument can be repeated with time. Of course, you go from being excited, we saw the back down, to not excited. And you go through a phase with, here you're excited, excited, excited. But all this is very quick. And then this is slow. It's slow. It wasn't drawn slow because it's supposed to be a small green arrow. It's slow because these little green, little arrows here, these little vertical arrows are slow. So you spend a lot of time here. And most of that time is spent in the refractory phase. And then eventually you get to the excited phase, excitable phase. So we see now the basic mechanism, which is that if you have spatial variation and diffusion and excitability, this is what is called excitability, is when you kick over a threshold, you go all the way to here, and you don't come back directly. That's what excitability is. So these ingredients, spatial variation, diffusion, excitability, leads to propagating waves. And this is the mechanism that is, or so I'm told, that is in the body. This is how cardiac waves, this is how the impulses in your heart move. And this is how neural impulses, nerve impulses move. So yes, in the heart in particular, you have the pacemaker, which is something that's periodically emitting electrical impulse, and they spread in one direction because of this property.
Physically, what controls the excitability?
Yes. I believe it's the 1/epsilon thing. I mean, does that answer your question? I'm not sure. I'm not sure I have an answer to your question, and I'm not sure this is the answer to the question, but does it seem to you like an answer to your question? Excitability is the fact that you need a mean, I can say in words what I said, but I'm not sure but I should have something better to say than the words I said. Excitability is requiring a threshold to go far away and eventually coming back. It's this phenomenon that we just described. That there's this red line here above which you must go, and then eventually you come back. But I'm not sure that's. You want to know what makes a system have equations that look like this?
Yeah.
Yes, right. I don't know. So now, if we go back, okay, so now imagine that we have a chain of x's, okay, and they are now reacting according to the whole reaction diffusion thing, with the f and g specified by these equations. Then that was what you were seeing in that film. That is to say, space acts like time. That's what a wave is, right? You move, moving in space is like moving in time. So let's go back to that. This is now, what is this? It is not a single point in time, as I was saying it was. It is instead, the value, here is space, x, and here's the value of u, and over here it's excited at u equal 1, and at u equals 0 it is not. And what you're following is that at any given instant, these are the values here. You see, you're just going round in the UV phase space. Corresponds that there. Yeah, this is the view in the UV phase space of this data that's u of x. Okay, these points they become excited because they're excited by their neighbors here. They get the value of x of their excited neighbor. Okay? So yeah, we said all that. Okay, and then we can do this in 2D and 3D, and there are those other simulations that we were just looking at here. Are there simulations or they're just pictures? I can probably get simulations somewhere. Are there? Let's see. No, I can't do right like this. I cannot do in Chrome. I have to do it in Safari. And so it's hit or miss. Yes, I want to run. So it's a property that they of these excitable media that they form these spiral waves. You have spiral waves on your heart. And that was the, let's see, is that which wave state is it? Plot type 2. What's plot type 2? Oh, it's just different colors. Okay, stop, and then what is this about the spiral state, disordered state? Are there two of them? Okay, the initial conditions were set up in such a way that it didn't form a perfect spiral. Probably there were several excitations. If you have a single excitation, then it will form a spiral. But if you put in a few, then it will form interfering spirals that annihilate the main image. And then, yes, all the demonstrations, it says, are in the same parameter values. This is a slightly modified one. So the excitation waves are spreading out. What's the clock type 1 like? It's black and white. So it looks more like experiment, right? Since it's black and white. Okay. We go back here. So you saw them in 2D, one can also see them in 3D. It's harder numerically, I guess it's probably harder experimentally as well. Okay, so I believe that's the end of the excitable media part. Yes, now we get to the second topic, which is called Turing patterns. Okay. Second part, we're going to, none of these things are completely disjoint from one another. They all deal with reaction diffusion equations, but different specialties, different phenomena. Okay, again, let's look at the homogeneous solution.
Sorry, Professor.
Yes.
That Turing pattern, is that from Alan Turing?
That's the same Turing, yes,
Oh.
yes, the same. Who knows who Alan Turing is? Everybody does. And now, it used to be, not that long ago, let's say, okay, Turing was in the 50s, and everybody knows his story now. He helped, he was one of the main people, according to the, who solved the code that the Germans were using in the war, and he was one of the inventors of computers, and he was a brilliant man. And his life was cut short by the fact that he was homosexual, and he was pursued by the law, and he was going to be imprisoned or given chemicals, and it's not sure whether he committed suicide or not. I think that's disputed maybe by somebody in his family. There was some poison taken, but there was some idea that maybe that he didn't quite mean to take a lethal dose. But anyway, his life certainly was made miserable by that. And his fame is relatively recent. I think that in the time that I was in school, people had not really heard of him. It was a kind of anecdote that few, and I don't just mean the movie. I mean, of course, the movie, you'll know, and that was just, what, 2 years ago or so, the movie? Something like that.
3-4 years ago.
Okay, but even before the movie, people had heard of him for the previous, I don't know, 20 years, say. So that brings us to 1995 or so. But his work was, after all, done in the 40s and 50s, early 50s. So between that time and between the 80s and 90s, he was, it was a kind of specialty that you knew about him if you were in certain branches of science, but he was not a popularly known figure. I don't know how much that was due to the prejudice about his homosexuality or what, but he was not well known until, I would say, the late 1990s, maybe 2000. We'd have to look that up. A group of people like you, even before the movie, I'm talking about, say, 5 years ago, would not have heard of him. But now, of course, everybody has heard of him. And that is the same Turing. And he invented so many fields of science that one can only imagine what he would have done if he had lived past the age of, wonders of modern times, past the age of
Oh, wow.
42.
I was going to say 40.
Yeah.
So young.
Yeah. And he lived past the age of 42. What might he have done? He would barely have died recently. He might even still be alive, but would have died maybe 10 years ago. And imagine what he would have done in all that time, given that he practically, sometimes, maybe it's a little bit of a hyperbole, invented computer science, invented some pieces of population biology. Imagine that. Very sad. Okay, so let us discuss then one of his numerous discoveries of his short life, Turing patterns. So let's again study the spatially homogeneous system. I mean, we simplify right now to the homogeneous system, and we found fixed points. This is not necessarily an excitable system at all. This is just, notice, to have excitability. We introduced a bunch of different definitions, perhaps they're being confused. Reaction diffusion equations look like this, but this says nothing about what the F and the G are like. If the F and the G are like this, pretty much where you can see that there's a threshold where you have to go past the red, when you have these kind of cubic nullines, that is when you have excitability. But that's a particular form for F and G. And now when we talk about Turing patterns, we're not talking about a particular form of F and G. So different topic, still in reaction diffusion, but not excitable media. So imagine in fact, we're back to the very beginning where we said, or even here, well, not quite, here we said, we have, for the homogeneous system here, we have fixed points, which are the intersection of V, F, and G nullifies, just the usual solution to F and G equals 0, and these are stable if the Jacobian has two negative eigenvalues, or eigenvalues with negative real part. So we're imagining such a situation. We have stable, supposing we have stable fixed point. Now we add on diffusion. The usual reaction, the usual thought is diffusion damps instability. Remember that if you have variation in your values, then diffusion gives your excess value to your neighbors. It generally has a damping sort of feeling about it. So you might think that if you were stable, without spatial variation, without diffusion, then you would be even more stable with diffusion. And Turing answered that question in the negative. There are circumstances under which you can be, this system by itself, without spatial variation, can be stable, but when you add the possibility of variation in U and V and diffusion, then you are unstable. Okay? Let's do the linear stability analysis. It's good practice. We're starting to get used to this. Let us write our perturbation, U and V, as the fixed point, U bar, V bar. That's the stable, homogeneous steady state, and it's got no x dependence because it's homogeneous, times some perturbation, U tilde, V tilde. As always, we don't want the complications of an actual geometry, so we're going to do the very simplest thing of plane waves. We have e to the I k dot x, so that means that diffusion just gives us a minus k squared, k being the norm of that vector k. This is a vector k dot vector x, because you could have variation in 2 dimensions. And we're going to find the sigma. The sigma is a consequence of the governing equations. So d by dt gives us a sigma, so we get sigma times u tilde and sigma times v tilde. That's a consequence of d by dt. And then the Jacobian, remember that's the linearization of this nonlinear function about u bar and v bar. We have, this is the derivative df du, df dv, dg du, dg dv. It's not written, but we are supposed to evaluate those at the fixed point u bar, v bar. Be careful to distinguish here between the bars and the tildes. These are tildes here, but we evaluate these. Remember the Jacobian, the partial derivatives are functions of where you evaluate them, and we're evaluating them at the fixed point u bar, v bar. And then when you do a linear stability analysis, any linear term just remains, and the diffusion is linear. And again, I remind you what linear means. It means that the function appears exactly once. And so this just remains when you linearize, and you do minus du Laplacian of this function. Laplacian of this function is minus k squared, bring down a minus k squared. So this is the action of diffusion on something of this form. Okay? So we can write that linear stability is always determined by the Jacobian. We can write the full Jacobian here, which is the Jacobian of the homogeneous system minus the diagonal matrix, diagonal as far as u and v are concerned, with minus du k squared minus dv k squared. Okay, and we can write it as 2 matrices here. If the, I've said I'm interspersing, and I think maybe it's at least as useful as anything you're learning about dynamical systems are little things I'm telling you about matrices and eigenvalues. I told you the formula for the eigenvalues of a 2 by 2 matrix. I said when matrices are block diagonal, the eigenvalues are in the blocks. I said if the matrix is upper or lower triangular, the eigenvalues are on the diagonal. So again, I'm going to tell you that the eigenvalues of the sum of this matrix are the sum of the eigenvalues of this with the eigenvalues of this. Is that usually the case? If I write, no, excuse me, that's not even this, I'm sorry. That's not the case, what I just said isn't true. It's true if these two are equal. If this is a multiple of the identity. We can just pull out a D and make this 1 and 1. And in that case, the eigenvalues are merely the eigenvalues of this minus the eigenvalues of this, which are along the diagonal. And why is that? Why is that? It's not usually the case. Why is this the case now? It goes back, we even said something about this in the very first class. We said it. We said it. We said it somewhere here. Yes? Okay, go back to the question that we were just asking. Why are the eigenvalues of this whole matrix, this sum of two matrices, equal to the sum of the eigenvalues if these two diffusion coefficients are equal? When are the eigenvalues of a matrix equal to the sum, excuse me, the eigenvalues of the sum of two matrices equal to the sum of the eigenvalues of the matrix? When can that be? Who here is in physics? Some of you are, I know. Okay, and who's taking quantum mechanics? And who has heard the phrase simultaneously diagonalizable? No, in quantum mechanics they didn't mention that? Okay. And what does simultaneously diagonalizable mean?
That has the same, the matrix have a same representation or the same basis.
So I'm same basis. Yeah, or can it be made to have? I'm sorry, I'm trying to lift the no. What did you say it was, Hugh? The advanced controls audio settings? No, surely not.
What are you trying to?
I want to lift this up to use the
Oh,
blackboard.
under lights, lighting.
Under
and
lighting, yeah. Ooh, under lighting. Wow.
Yeah.
Lighting, room settings. Yeah.
Right
Okay.
screen.
I see. Right screen up. There. Okay. So you were saying it's the so you have the same. You can have the same basis. Yes. Okay. Right. And when that's right. And when can that happen? When can two matrices have the same eigenvectors? Do you remember when that is? They have to commute. Okay, and that is behind a lot of the properties that we saw. Symmetry in the symmetry class. That is to say, you remember we said that equations were said to respect the symmetry if the evolution operator commuted with the reflection operators or the symmetry operators. Right. Okay, if they commute, then they can have the same eigenvectors. And eigenvectors of a symmetry operator are things with symmetry or things with a certain, well, anyway, that's behind a lot of it. Yes, indeed, we need to have commutation of these two matrices in order for their eigenvalues, in order to be able to just add the eigenvalues, in order for them to have the same eigenvectors. And everything commutes with the identity. This isn't the identity if these are different. That's enough diagonal isn't enough. But if they are the same, then this is the identity, and hence everything is an eigenvector of it. Remember, that was what was in that set here. If you take the identity or a multiple of the identity, then everything is an eigenvector of it. It has a two-dimensional eigenspace. Everybody's an identity of it, an eigenvector of it. And that is because it goes together with the fact that it commutes with every operator. And so if these two commute, then any eigenvector of this one is also an eigenvector of this one, since everybody's an eigenvector of this one, and hence all you have and it has a single eigenvalue, which is minus k squared d. And so you just take whatever eigenvectors you had for this, and it's also an eigenvector of this, and the eigenvalue is altered by just minus k squared d. Okay? Hence, if the two diffusion coefficients are the same, then you cannot have a Turing pattern, okay, a Turing instability, as it's called. We'll get to that later. Because if you're stable in a homogeneous way, then you're even more stable when you put in diffusion, which is the intuition.